Hello, my name is Andrew Fulbrook, Director of Global Powertrain Forecasting at IHS Automotive, and today I'm going to introduce to you something called the global test cycle, or the concept of the global test cycle. Before I do it, it's important to mention to you that this is an opportunity for me and us at IHS Automotive to introduce the idea that we go beyond the numbers in the automotive group, and in the powertrain group it's more than just producing a forecast. So what lies behind the light powertrain services on the website that you're currently looking at is a lot more qualitative consideration, and this is one of the areas that contributes to that qualitative consideration. So the global test cycle then, what is it? Well, it's a convoluted, confusing, mad, crazy world actually that touches on various issues such as political issues. It's very scientific, and it's also steeped in engineering as well. Before we get into the main body of what the test cycle is and some of the issues surrounding it, we'll talk about something called the 5 stars of convergence. These are areas that we've witnessed in the automotive industry that are coming together regardless of where we are in the world, safety and engineering, etc. We'll touch on that. Then we'll have a look at why, or one of the prime reasons why we're looking at developing a new global test cycle. And that's because at the moment the current test cycle is pretty inconvenient, whether it's in Europe or in the US or in Asia. It's inconvenient for the OEMs and it's also inconvenient for the customers as well. Then we'll really get into the discussion about whether the current suggestion of the WLTP is a serious solution or not. We'll touch on some of the technology effects, and then we'll finish with a brief summary. So these are the 5 stars of convergence that I was talking about. And so what we're really seeing is a global convergence, regardless of where the vehicle is built or sold, regarding safety, environment. Vehicle platforms are becoming common and modular across the world. Powertrain platforms, engines and transmissions and alternative propulsion systems are becoming more and more convergent. Fuel quality as well is gradually becoming standardized around the world. So perhaps one of the last areas is our area of homologation. So this is really important because this is what you see when you walk into a showroom as a consumer. You're making a purchase decision based on the fuel economy or the CO2 of that vehicle. And that is derived from a very fixed, rigid test procedure that are very different around the world at the moment. And there's a definite goal to try and get those converged around the world. So just some proof or some evidence, if you like, of where some of that convergence is taking place within those 5 stars. The legislative environment, or the CO2 legislation, or fuel economy legislation. We can see in the early years here, we were poles apart. Poles apart. You can see the US, quite poor performance compared to the rest of the world in terms of their fleet CO2 or fuel economy averages. But even the US, with some fairly big changes, and now that Obama has been voted in, by the way, we're likely to see this stringency continue. There was a risk that it might not be that way if Romney got in. So we can see that particularly out in the late 2020s, we're all beginning to converge in terms of what the OEMs need to achieve for their CO2 performance. Now, of course, at the moment, these are all based on different drive cycles. So the rolling roads are different, the laboratory temperatures are different. So they're not actually an apples-to-apples comparison at the moment, but we will get there with the WLTC. But what does this mean? Well, this means that we're getting to a point in that kind of long-term time frame where we can truly begin to consider the notion of a global engine. So an engine that you can build in Italy, for example, and then go sell that immediately in China. At the moment, OEMs are having to gear their vehicles, gear their engines and their technology choices to those particular markets as a function often of the test cycle. Very quickly on how we're beginning to standardize the fuels. These are a range of test fuels. So we have EU5, so this is the specification for the test fuel in Europe. When we say test fuel, this is a very different set of specifications to what you see when you go to the pump and you fill up. These are standardized, homologated test fuels. This is the US here, EPA current and EPA proposal. California, like it does in many occasions, has its own set of rules, which are generally far more stringent than the rest of the federalized US. Then we have Japan 08, JC08 here, and Brazil right at the end. And I've included Brazil because Brazil has decided to launch CO2 legislation for the first time ever. So the OEMs will be held accountable for certain performance of CO2. But you can see that it's got quite a long way to go before it can begin to perform like the Europeans. Particularly draw your attention to the sulfur limit here. Brazil has a sulfur limit in its reference fuel of 800 parts per million, whereas in Europe and in Japan it's under 10 parts per million. What I'm trying to point out to you here is until we have a standardized global reference fuel specification, we can't use different fuels and expect the same results from our engine performance. For example, if you took a US gasoline fuel and you put it in a European car on the European cycle, the NEDC, the new European drive cycle, you will get different emission results and different engine performance than you would from a European spec fuel. That's because you have to add additional protection equipment to the engine to cope with some of those poorer specifications of fuel. So fundamental to the debate on WLTC is the ability to produce a standardized reference fuel. So why are the current test cycles so inconvenient? And this is the first of a few speed traces here, so you're going to have to stay with me as we go through the rest of the presentation. It can be fairly hard going. The first thing you notice is the difference. I mean, it's completely different between Europe up here on the top right, Japan, and the US down here at the bottom. Different for a couple of reasons. Different because the maximum speed points are different. The duration of the cycles are different, particularly between Japan, Europe, and the US. The US runs for 2,600 seconds, the vehicle is on its cycle while it's being tested. In Japan and in Europe, it's about 1,100 to 1,200 seconds. But also, one of the key fundamental differences here is the difference between a transient or a constantly changing cycle, which is what we see here in Japan and in the US, and a very predictable, steady state cycle that we have here in Europe. And we can see that it's incredibly easy for an OEM to calibrate his vehicle and his engine technology to this very blocky, steppy cycle, unlike Japan and the US, where you have much more torque fill requirements as you go through the cycle. So that's become particularly inconvenient for an OEM. That's because if he wants to sell, for example, a Toyota Prius in Europe and a Toyota Prius in Japan, you will get much better fuel economy performance when you sell that in Japan compared to Europe, because most of the cycle, or vast chunks of the cycle in Japan, are spent under a 30 km/h speed threshold. That's where the hybrid system on a Toyota is operating, that's where it's working. If you apply that speed threshold to Europe, a lot of the chunk, particularly the highway mode at the end, is spent over that cycle, so the engine is having to cut in. So you get a different fuel economy result for the Prius in Japan than you do in Europe. And OEMs don't like this, because this costs them money, especially when you come away from the hybrid idea and you're looking at regular vehicles. Perhaps you need a new technology to govern or to combat this cycle, or you don't need a technology for the European cycle. It costs OEMs money to calibrate to the different cycles. When we get to consumer response, we've actually seen just this week some issues in the US with Hyundai, or Hyundai Kia Group, where consumers are saying, hey, this is not the kind of fuel economy performance that I was expecting to get when I bought this vehicle. And in the US it becomes a lawsuit, or a potential lawsuit. It's not quite as serious as that in Europe and Japan, but it's very real, and it's this difference between what you've been expecting to see when you buy the vehicle and actually what you do experience has been going on for a number of years. This is the European example. So what I'll draw your attention to is two lines, the orange line and the blue line. What this blue line shows you is ADAC, which is the largest motoring organisation in Europe, based in Germany. ADAC have taken a baseline of type approval figures, so these are the official certified CO2 figures across a range of vehicles in Europe, and that's indexed there to 100%. What they've done is they've created their own test cycle to try and replicate more real-world conditions, to try and make it fairer to the consumer when he buys that vehicle. And we can see over time, what they've done is they have used the actual weight of the vehicle while it's on test. At the moment, OEMs are allowed to use the lightest vehicle on the family, which is a bit of a cheat. But if the hole's there, you'll exploit it, right? So at the moment, BMW, for example, I always use them as a really good example, but perfectly allowed to do this. They will submit BMW M3 Coupe, for example, which has a V8 engine, lots of leather, lots of air conditioning, lots of nav equipment, it's quite heavy. They will allow to use the reference weight of a BMW 318 base, so no equipment, light engine, small package. That is not truly representative, because what happens is when that M3 goes onto the chassis dynamometer, the rolling road, the technician in the laboratory will set the rolling road to a resistance based on the weight of the BMW 316, not based on the weight of a BMW M3. So your M3 starts to look pretty good in terms of the CO2 performance. What ADAC have done is use the actual weight. They've also decided to turn the air conditioning on at 20 degrees C. We all pretty much have air conditioning on, even in the winter. We like to have it on just to keep us nice and ambient. The issue is in Europe on the NEDC, you're allowed to turn the air conditioning off. You don't have to put it on the test. And air conditioning, of course, is a drain on your fuel economy. So these two things combined make it a little bit more realistic. And when you do that, you begin to see still an 11% difference between type approval number and the better representation of real-world conditions. That's scientific. The totally unscientific number is Sprint Monitor database in Germany, which has about 28,000 vehicles of all shapes and sizes. This is real-world consumer information that's being passed back to ADAC. Completely unscientific, but in the real world we see the delta at about 20% difference between what you thought you were going to see when you bought the car and what you're seeing now. So we can say with a certain degree of certainty that at the moment in Europe there's between a 10 and 20% difference between what it's stamped on the vehicle and what you're likely to see. And that's a function of a drive cycle that is no longer representative. In fact, it never really was. So, is the WLTP a serious solution? And in fact, I'll stop here and explain some of the acronyms. You're going to hear WLTP, you're going to hear DTP, you're going to hear DHC, and you're going to hear WLTC. WLTP is the name given to the revamped procedure. So everything, including the cycle and the laboratory test conditions itself. WLTC is just the cycle. DHC and DTP I'll explain as we go through the next portion of the presentation. So let's first remind ourselves of the objectives of the WLTP movement. It's to remove those technical barriers on the different markets that I spoke about. For the OEM, it's to reduce calibration costs and methodology development. It's to introduce globally relevant technology. We saw that we're getting close to the concept of a truly global engine. It's to allow for direct international comparison at a governmental level. Key for the consumers, it will reflect the real-world driving conditions better than the incumbent cycles do at the moment, and it's to benchmark national performance, again, at a governmental level. Who's taking care of this work? Thankfully, not us at IHS, because it's a huge amount of work. We're very interested in it, and of course, as I said, it bakes into our forecasting methodology, but it's the UN that are running this program. The working group is ingeniously titled the Worldwide Harmonized Light Vehicles Test Procedure. Very catchy title, great if you can have that on your job card or on your business card. WLTP, there's the P for the procedure. That effort is split into two working groups, the test cycle, the DHC working group, and the test procedure, the DTP working group. Split from the DTP working group, you have people working on a new laboratory procedure for regular engines, internal combustion, and a group that are working on lab procedures for electric vehicles, because these have to be treated very separately. We saw that issue with the Prius. But I'm only going to focus on the DHC element today. This entire function here will complete its work by 2014 as part of Phase 1. As I said, I'm only focusing on DHC, but I will treat you to a couple of insights on DTP at the end of the presentation. So Phase 1 runs to 2014. We're around 7 months, I say we, not IHS. The United Nations is about 7 months behind in its working group effort to complete Phase 1. DHC, as I said, I'm going to talk about today. DTP is looking at things like how can we better measure particulate mass and particulate number. Volatile compounds, for example, ammonia. The lab procedure for the EV, how do we prepare the vehicle, how do we configure the laboratory. All of these things are being worked on, and finally, you remember I was talking earlier about this drive to get a global set of standardized reference fuels. That work is being looked at as well. Phase 2 began this year and will run till 2016, and that's looking at things like mobile air conditioning procedure. So how does the aircon in our vehicles contribute or not contribute to our CO2 performance? The ambient temperature of the laboratory itself, we've got a couple of interesting pieces on that at the end of the presentation. there are various countries around the world that have higher altitudes than the Europeans or the Americans. So how do we cope with that? How do we capture that in our test cycle? And particularly in-service conformity, this is extremely important. This is the idea that we're producing a new type approval procedure and cycle, but how do we know that a manufacturer won't try and cheat that system, and once it's gone into the market, we don't know if it's performing as it should be? So this is a notion where those vehicles, after a couple of years, will be called back, probably during service time, rerun on the WLTC using mobile units to see whether the OEM is in conformity or not. And if he's not in conformity, there is a notion of paying fines out at this point. So this is closing the loop on manufacturers trying to manipulate the system. So phase 1 calls for completion at the end of 14. There's a notion that the new laboratory procedure could be used in Europe as early as 2014, not the cycle, just the new laboratory procedure. We're unlikely to see any of this come into the market before 2020. Japan and Europe are vying to be the first markets to bring these into service. Probably will be the Europeans, closely followed by the Japanese. Chinese and Indians will follow. It's not yet clear whether the US are really going to go with this idea, and there are various reasons why, and I hope to explore that in the rest of the presentation. So, I'm not going to spend too long on these slides, but it gives you an idea of where we are, again, where the UN is in this process. We have our current version of the cycle, WLTC, C for cycle, version 5. That is going through its second validation test at the moment, and I'm going to show you some of the results of the early second validation test. Absolutely crucial items that are still being discussed are the cycle profile, and we'll touch on that. The weighting factors, again, trying to get India and the US, which have very different drivers and very different vehicles, onto the same cycle is proving extremely difficult, and I thought we all thought that would happen. Gear shifting, at the moment most cycles have predetermined gear shift points based on vehicle speed, and again that allows the OEMs to calibrate their transmissions and their gear ratios to maximize the fuel efficiency. Doesn't necessarily mean that the customer is going to drive that way. So we're looking at that, and we're also looking at low-powered vehicles. How do we capture vehicles that have no more than 40 or 50 horsepower on a cycle that a BMW M5 will also be going on? It's far easier for a BMW M5 to follow those high speeds than a Maruti Suzuki, for example. So here comes the fun part. This is where we start to get technical, and we start to get into the world of engineering statistics. I see you're all gripped by that prospect. So, how do we even think about creating a worldwide harmonized test cycle? Well, first of all, if the objective is to try and replicate the real-world conditions as best as possible, then we need to understand what the real-world conditions are. How do people drive? What do the cycles look like? What do the average speeds look like? So what we've done, or what the UN has done over the last few years, is it's created 665,000 kilometers worth of driving data from all of these countries: Japan, South Korea, India, the US, and Europe. Europe's contributed the most, but Europe is largely pushing this along with Japan. I've ordered the flags here in terms of the dynamicity of that driving region. What do I mean by dynamicity? Essentially, what dynamicity means is the acceleration distribution width and the speed distribution width that we're seeing in those driving cycles, or in that real driving data. We know that the US is the most dynamic driving region. In other words, the accelerations are quite hard, the decelerations are quite hard, the average speeds are pretty high, and also there's a lot of flux between low and high speed as well, bunched up quite quickly. So the speed distribution is quite wide, along with the acceleration distribution. What we've seen with this real data is India is the least dynamic. Very shallow acceleration inputs, very shallow deceleration inputs, not particularly high speed and then falling to low speed. So it's a fairly shallow distribution width for India. So all of this data has been gathered from inputs from these regions, so we now have a pretty good understanding of split between urban, rural and motorway duty cycles, what the characteristics of that driving nation look like. But of course it's unfair to go any further in attempting to produce a cycle without weighting those different areas of urban, rural and motorway, because Urban in the US, for example, might be something completely different to urban in India. Urban in India, you're probably not really getting out of second gear. You're probably not going that much faster than 20 or 30 kilometers an hour. So the first thing we have to do is abolish the notion of urban, rural, and motorway, and use the speed as our governing body to split the cycle. So we're looking at low, medium, high, and extra high speed phases. And then using that in-use data, which we'll call WWW for the rest of the presentation, we can begin to weight or put coefficients in there to make sure that we've got a fair playing ground before we begin to produce our test cycle. Right, the wonderful world of chi-square, and we all love a bit of chi-square. What's really important to make sure that we're picking the most representative data points for the low, middle, high, and extra high speed phase is once we've unified this data and got it all together, we run a chi-square analysis on each of those. So what chi-square does is it allows us to pick two sets of data, the expected data and the observed data. This is our expected data. This is what we're expecting to see because it's in the in-use data. And our observed data, which would what would be WLTC would show us. And it allows us to take the most statistically representative data point when comparing those two. It's very similar to sort of best fit analysis. And a good and real example that I can give you, if you're struggling with chi-square, is there are 2 periods throughout the year where I should be buying my wife flowers. 2 periods, our anniversary and her birthday. That's the expected data. She expects to see flowers delivered to her twice a year. But I'm a man, so I'm likely to forget on at least one of those occasions. So you run a chi-square on there, and you'll be able to see, is there a statistically significant difference between her expectations and what she's seeing, or is it just pure chance that that's happened? In this case, am I just a bad husband? So we're taking 2 points that are as closely matched as possible to make sure it's statistically significant. We're going to come back to chi-square a little later with a fancy equation on there to show you as well. So first, we're going to have a look at the speed distribution that I was telling you. Speed acceleration and speed times acceleration distributions are the parameters known to have the most impact on air pollution and fuel consumption. So our in-use data, this is our raw in-use data, taking the least chi-square number possible, which gives us the best statistical representation, we can see that actually our speed distribution frequency for Asia and Europe is actually pretty close to WWW. We need to make sure that if we're going to base an extremely important test cycle on the in-use WWW data, it needs to be representative of the regions that we formed it from, right? So we can see that the average global number is very similar to Europe and Asia, but the US number, there is a much bigger gap. There's a much wider speed distribution in the US than there is with some of the other regions. So whilst with the low speed phase we're seeing some difference in the speed distribution between the US and the other regions, which means, actually at this point, we can't really say that the US is very well represented if we followed this pink line, this WWW number. It gets a little better when we get to the medium phase. So we've managed to get some correlation there with a medium speed phase distribution. The high and extra high speed phases I won't show you today because we didn't get any data from the high and extra high speed phases from Japan or the India or China because they don't really drive at high or extra high speed. So we've taken the US and European experience and that's how the UN has created its high and extra high speed phase. Acceleration, this is absolutely key as well. So the low speed phase, again, we can start to see that we're trying to follow this pink line in terms of best fit or best representation. We can see that Asia has got a slightly wider acceleration distribution in the low or in the deceleration phase, and it's fairly tight. Europe is extremely tight to the worldwide average, but again, you've got the US. Very difficult to try and pull the US into the global test cycle at this point, and it shows that that dynamism that exists in the US is really not very well reflected in that WWW data set at this point. This is the key one, the vehicle times acceleration, or the vehicle multiplied by acceleration frequency distribution. This gives us a really good insight into the national driving characteristics of that country. How hard do you put on the gas, how hard do you brake, how fast do you go, and how slow do you go. This is absolutely key, and again, we see that the US is not quite tallying up with the rest of the world. So we've got a real issue with the US here in terms of representing it for WLTC. So we're beginning to see that one size does not fit all, but we've seen many, many times that there's always a good effort to try and do so anyway. So what do we do? Well, this is the process where we've managed to produce the global test cycle. And we take those in-use driving behaviors that I showed you. We then apply various weighting factors to squeeze and bend and shape that US driving profile to get it as close as possible through massive statistical manipulation to get it as close as possible to Europe and Asia. And that happened. We then combine the short trips. We do our least chi-square base number, or we do our chi-square base analysis. We compare other comparisons or other parameters, and we get to our common test cycle. That common test cycle is based on that www in-use database, although I said it's been bent and stretched and changed to try and get it as close as possible to the other markets. The length has been set at 1,800 seconds. That's how long the vehicle will be on test during the WLTC. And that's very similar to the heavy-duty cycle, which is already globally harmonized, and the worldwide motorbike test cycle. And 1,800 seconds has been determined as a pretty good length to get enough data to test the vehicle enough, but it's also key that it's repeatable within the confines of the laboratory. The short trips and idling periods have been selected from www. And again, it represents the best statistical representation of those most important parameters: speed, idle, acceleration, and speed times acceleration distribution. This is where we are. This is what you've all been waiting for, I'm sure, with bated breath. The WLTC version 5. Here are our 4 speed phases: low, middle, high, and extra high. 1,800 seconds in total, a maximum speed of 131.3 kilometers per hour, and the vehicle will travel a distance of just under 23 kilometers whilst it's being tested. Already, you can begin to see why you get a bit of backlash here, or a bit of feedback, let's say, from Japan and India. The current maximum speed on the Japanese test cycle is 85, 86 kilometers an hour. We're now asking the Japanese OEMs to follow a speed trace that hits 131.3 kilometers an hour. I've been to Japan many times. I've never seen anyone travel 131 kilometers per hour. And there are many vehicles in Japan, and particularly India, that will struggle to try and get to that speed because they don't have the size or the technology there that the Europeans and the Americans do. So we can begin to see already that this might cause some problems. In fact, buckle up, because we're going to go into some speed trace feedback from Japan and India. This has actually been led by Japan, and Japan has said, okay, got some issues with this. We've taken some typical vehicles and we've put it on the WLTC version 5, and here's our feedback. For a start, this speed point of 12 kilometers per hour needs to be dropped down to 10 kilometers an hour. That's because, particularly in India, first gear is so deep we can't actually get to 12 kilometers an hour in first gear. We can only get to about 9 or 10 kilometers an hour. So maybe we start the test in second gear, which is completely unacceptable. We have to start the test always in first gear. So there's some manipulation required here and some negotiation going on. There's some smoothing. There is one point that's key here, and I'll show it to you here. This is as we get towards the end of the test. Japan has raised huge concern that between 1,550 seconds and 1,750 seconds, the vehicle is required to maintain a steady speed at 120 kilometers per hour. It's never happened in Japan on a Japanese test cycle before. This is a completely new world. It means redoing all of the technology, potentially. It means recalibrating the vehicle, transmission changes, engine changes, vehicle changes. There is huge concern, particularly from Japan and India, on this point. So we can begin to see, and I'll skip this slide, we can begin to see that even though we've done our best with chi-square, we've done our best manipulation, our best squeezing, we're still not quite there to produce a test cycle that's fully representative of all the markets. And this actually shows us that, remember, we're trying to get our lowest chi-square number possible. That gives us the best confidence in the best statistical fit between the real data and what we're trying to simulate with the WLTC. And we've seen that critically for the low and medium speed phases, our chi-square number hasn't really changed between version 4 and version 5. You can see that in the red boxes there. So more effort is required to get that chi-square number as low as possible. So here it is then. Chi-square is a sum of your observed data minus your expected data squared over your expected data. Everyone knew that. And as I said, it compares the difference between the actual frequencies and those which one would expect if no other factor other than chance would have been operating. So we'll call it the significance test. I keep going on about chi-square, but it's fundamental to finding a representative test cycle. The null hypothesis is a hypothesis that suggests no statistical significance exists in a given set of observations. So if we understand the chi-square value, it allows us to accept or reject the null hypothesis. Any chi-square value under 3.84 or 3.84 and below allows us to accept the null hypothesis with a 95% confidence in our decision. So we're looking for chi-square numbers under 3.84. So we go back and we stretch and we bend and we try and get the cycle to be as representative as possible again with various weighting coefficients and little cheats here and there. And where are we at the moment then? This is as far as the UN has come at the moment, at this stage. So this is our acceleration and our speed distribution map for WLTC version 5. Under 3.84 we're looking for, and then we can be very confident that it'll be very well represented for the real world. Europe looks great. The US now looks really good. Well, actually, it looks like we've swung it way too much in favour of the US because now India, Japan and Korea, the chi-square numbers are way too high. We probably can't do any more statistical manipulation now. We're probably tapped out. We're probably finished. So we now need to overlay other coefficients or other weightings to try and allow the Japanese and the Indians a safe passage through the new test cycle. I'm sure you've been scratching your heads throughout this presentation. You've been thinking, well, what happens if you do put a Japanese or an Indian vehicle on the unadjusted WLTC version 5? Well, this is what happens. This is what the Japanese consortium decided was a typical vehicle for Japan. It was actually a 600cc, 3-cylinder CVT transmission A-segment car. Tiny box car. Now, Japan does produce and sell those kind of vehicles, but it's not actually fully representative of the sales market in Japan. These get a lot of B and C and crossover vehicles, and you have quite a few D-segment cars in there as well. But this is where we get into the realms of politics, where Japan is trying to negotiate, quite rightly, and it's saying, okay, for the first 1500 seconds of the cycle, it wasn't too bad, okay? It wasn't too bad until that speed started to go up and until the acceleration distribution needed to start getting more aggressive. And at 9 points between 500 seconds and 1500 seconds, the engine went into complete protection mode. In other words, the engine got too hot. It changed the air-fuel ratio mixture in the engine to protect the catalyst and the exhaust system from going south, essentially. And when your engine goes into protection mode and your vehicle starts to go into protection mode, your CO2 emissions and your fuel economy go out the window, essentially. It's very harmful for CO2 and fuel efficiency. And of course, the whole point is to get good representative CO2 here. So at 9 points, and a really good one to look at here is at around, where are we? Here we go. Around this point here, between 500 and 1,000 seconds, the vehicle is doing nigh on 6,000 revolutions per minute, which is quite a high engine speed, and it's achieving a speed of 60 kilometers an hour, which means this is a incredibly low-powered vehicle to try and put on a cycle that the big stuff is going to go on as well. So it's really not a fair representation. They've chosen a very small vehicle to make their point, but the point is still very, very valid. So we can't possibly have vehicles going into engine protection mode. So a couple of slides ago, we noticed that actually it's pretty much impossible to get all of these different types of vehicles for all of the different countries onto one global test cycle. And I was talking about measures that we need to take to overlay the cycle to make it a fairer playing ground for those different regions. Well, here's one idea. One idea is, why subject these tiny cars to the full speed trace, the full acceleration trace of a BMW M5 or an X5 or an X6, for example? So the UN has proposed this as a potential overlaid solution. If your vehicle, you as an OEM, is 22 kilowatts per tonne or less, and it can travel no further or no faster than 70 kilometers an hour, By the way, 22 kilowatts per tonne is extremely low. There aren't that many vehicles that have such a poor power-to-weight distribution, power-to-mass ratio. I'm still on chi-square, you see. If it's 22 kilowatts per tonne or less, 70 kilometers an hour or less, you only have to do 3 repetitions of that very short low-speed cycle. That's much fairer. That's much, much fairer. If you're 22 kilowatts per tonne and you can go over 70 kilometers an hour, which is doubtful, to be honest, because with that power, you're not likely to get that speed. But if you can, you do 1 low and 1 medium speed phase. Again, that's far more representative of that kind of vehicle. If you have a power to mass ratio of 34 kilowatts per tonne or less, and you can travel no faster than 90 kilometers an hour, you do 1 low, medium, and a low. And so on and so forth. Let's cut to the chase. If you have a vehicle that's producing 34 kilowatts per tonne or over, and the vehicle can travel faster than 135 kilometers an hour, you do the full trace. Low, medium, high, and extra high speed trace. Wouldn't it be interesting to take the IHS automotive data that we have with power and with mass, and to try and see how many of our vehicles sold in 2020, when we expect this cycle to come on stream, will be subjected to which class? Class 1, Class 2, or Class 3? And then we'll begin to answer whether those vehicles that India and Japan picked are truly representative of the market. And we can answer that with, actually no, they weren't particularly representative. Our data at IHS Automotive Powertrain shows us that in Japan 2020 sales environment, 99% of the vehicles that will go on sale in 2020 will be subjected to the full Class 3 speed trace. In India, we do have much lower powered vehicles, very small A-segment cars, but still 84% of the vehicles sold in India in 2020 will be subjected to that full Class 3 speed trace. Comes as no surprise that in Europe and in the US, practically all of the vehicles will be subjected to the full Class 3 speed trace. There's some witty comments in there about autobahns and supercars, but I don't have the time to crack those jokes. So now we know, and we're coming towards the end of the presentation, now we know that most of the vehicles will be subjected to the full Class 3 speed trace. Why don't we take the full Class 3 speed trace and acceleration distribution, which is here in blue, this is the WLTC version 5, and let's overlay our current test cycle to see where some of those differences are. And if we can see where some of the differences are, we can begin to have a pretty good stab at the technology changes that are likely to come about. So I'm going to run the JC08 cycle. Here it comes, it's coming across. I might just run it once more. Let's take it back and run the current JC08. So this is Japan. I'm not overlaying the Japan acceleration distribution. Just let's focus on blue versus green. And we'll focus on a couple of things. The first thing we'll focus on is this critical early phase of the vehicle when it's on the test, the first 120 seconds. Why is that so critical? Well, during the first 120 to 200 seconds, when a vehicle is on a cold test, so it's wheeled into the laboratory is at ambient temperature, the engine's pretty cold. The catalysts need to be lit off, as we call it, as fast as possible to get your CO2 down. And that's because in this very early part of the vehicle on its test, this is when it produces the majority of its emissions, when it's cold. So we have lower engine loads now. If you can see the blue number, or the blue trace, is a lower portion of that time, or a portion of that time is spent at a lower vehicle and engine load than the current JC08. Thereby, that leads us to an increased focus on lighting off those catalysts for Japanese vehicles even more than we're doing now. How can we do that? Well, years ago it started with underbody catalysts, and then we moved those catalytic converters closer to the manifold. Then we put them as close coupled manifolds, so a part of the exhaust manifold. The only thing you've got left to move that catalytic converter closer to the explosion in the engine, which is what you want to do, is by casting the cylinder head with the catalyst inside it. And that's already started to happen with Volkswagen, but and others, but it's a very early kind of technology, an early kind of trend. This is likely to potentially accelerate that trend, particularly for Japanese vehicles, even more. I would also point out, even though you can't see the JC08 acceleration distribution, I can tell you that this is far more dynamic than the Japanese acceleration distribution. Therefore, we could be looking at the notion of bringing in new torque field devices such as mechanical electric boosters on mild hybrid. And this is because, just because we have very steep acceleration and very steep deceleration, to get that steep and sharp and quick acceleration, why does we necessarily need to have a human putting his foot on the accelerator pedal? Because we've got so many of these events now, particularly you can see these very, very quick, fairly shallow torque fields, or torque breaks, we could be looking at a mechanical or an electric supercharger to fill that torque in, instead of necessarily a link between the foot and the gas. That could be an interesting function of the move to WLTC in Japan. Here comes NEDC. In Europe, you can see here's this blocky, steady-state modal type of trace. Again, it's very different to the WLTC. And again, we have a similar situation. This is more dynamic than the NEDC in terms of the acceleration distribution. So again, we could be looking for almost definitely new calibration techniques so that the engine is kept within its optimum operating area, because when you keep pushing the gas and decelerating on an engine, it's very difficult to try and keep that engine within its emissions operating mode. And this time we have a reduced cold start effect due to a longer cycle. So here's one more tidbit for you. The longer the cycle, the lower the CO2 emission, generally, because it reduces the impact in this really critical early phase, because a lot of the cycle is then spent out here. The shorter the cycle, the more emphasis on this cold start effect. So there, naturally, because you've got a shorter cycle, you'll have a stronger emphasis on protecting CO2. And in the US, this is going to be a real problem, because here comes the US speed tracing. It's just going to keep going and going and going and going, right up to 2,400 seconds. We're going to be shortening. If the US takes this cycle, we're going to be shortening that cycle significantly. So that immediately puts more emphasis on this cold start area, which immediately opens up the OEMs and the engineers to have to focus on engine protection equipment and after treatment for that cold start area. And I will just make that point by bringing that onto the slide there, so we can see some deeper technology adoption. Right, I'm going to try and come to the end. So what do we know in terms of the impact on CO2 and non-CO2 emission performance by moving to WLTC? Well, the engine operating area, or the map for engine speed and engine load, is larger on WLTC than it is on NEDC, for example. Therefore, small downsized engines, diesel and gasoline, could become more challenging to depollute. That could, in the process, harm fuel consumption, ironically, and make the Euro 6b, but particularly the Euro 7 norms, quite challenging. However, after all of this rhetoric from me about how important this WLTC cycle is, what do we know when tested in Europe? The JRC, the Joint Research Centre, part of the European Commission, and ASEA, they've taken vehicles that are in the market now and put it onto WLTC version 5 to see what the difference is in CO2 of typical vehicles on NEDC and typical vehicles on WLTC version 5. The difference has been around between 4 grams per kilometre and 7 grams per kilometre. It's not massive. So what this tells us actually is we must summarise the effects of the cycle versus the effects of the test conditions. And if I'm lucky enough to give you another instalment of this, we'll be talking about the test procedure in more detail. But very, very quickly, there are 5 key elements that will govern CO2 and non-CO2. Non, not on. The dynamicity of the cycle. We know that the WLTC cycle is more dynamic than any other cycle apart from the US. So that will automatically lead to higher CO2 emissions if you change nothing else. The higher the average speed, the lower the CO2 emission. That's because CO2 follows a U-curve. There's very high CO2 at the front and very high CO2 at the end of the cycle in a U-curve. But in the middle, you have a pretty good sweet spot where the CO2 is relatively low. And WLTC has a higher average speed in all cycles, so that will not lead to higher emissions. Percentage of idling periods. All emissions are measured in mass over distance, grams per kilometre, grams per mile. If an engine is on and the vehicle is not actually travelling any distance at all, then the higher the idle ratio, the higher the emissions. That's why you see so many stop-start vehicles in Europe, because it has the most or the highest percentage of idling period on the cycle. It's an easy one for OEMs to put stop-start in there to try and combat that. WLTC now has a lower idle ratio than all cycles, so that does not contribute to higher emissions. We know that the longer the cycle, the lower the CO2 emissions. We spoke about that. And finally, my point, test conditions. Road load, the mass of the vehicle, remember my M3 example at the beginning. Temperature, gear shift, auxiliary operation, remember my example about air conditioning. Reference fuels are all being reviewed. And I will draw your attention just to two things before we finish the presentation in terms of the procedure itself. This is what the WLTP part is looking at. At the moment, comparing Europe, it's based on the lightest vehicle of the family. We're now going to switch that to the heaviest vehicle of the family, not the lightest. The ambient temperature, at the moment, the OEMs in Europe are allowed to set their laboratory between 20 and 30 degrees C. But the OEMs are allowed to do their own tests if no one knew this, so there's a lot of trust involved here. Between 20 and 30 degrees C. It would be great if Europe was bathed in 30 degrees C. It's not realistic ambient temperature. So the WLTP setting is for 25 degrees plus or minus 2 degrees C. In fact, the European body is asking for an ambient temperature setting close to 15 to 18 degrees C, which is far more realistic for the European temperature. This is absolutely key, of course, because if you lower the ambient temperature of the laboratory, it takes longer for the vehicle to warm up, which impacts your CO2 emissions. Why do we think? I would imagine most OEMs in Europe set their temperature at 29.9 degrees or 30 degrees. The higher the ambient temperature, the faster the lubricants get more warmed up, and the faster the engine comes up to speed. So what do we know? The US and Europe in-use data now seems to correlate well to WLTC version 5. We've still got some work to do for Asia. It's a very complex, if you hadn't have guessed, political process with well-founded intentions. We're not likely to see this come into play until 2020. Probably that the revised procedure will have the same, if not a stronger impact actually, than the new cycle itself. What work remains, we have to construct the mode for cold start and hot soak tests. Weighting factors to develop for those 3 class parameters. You remember I was talking about 22 kilowatts per tonne, 34 kilowatts per tonne. Those are still up for negotiation. We can change those somewhat to make it a bit fairer. Accounting for vehicles that cannot follow the entire speed trace. We saw an example where we just about managed to follow that speed trace with a typical Japanese vehicle. I've seen tons of information where the vehicle could get nowhere near the speed trace. So we need to account for that. And we should have a conclusion to the procedure by Christmas of this year. So the new drive cycle is coming. Are we ready? No. Do we consider the implications of this when forming our powertrain forecasts at IHS? Yes, and that's true for the big services, and it's also true for the light services. So thank you very much for your attention. Thank you.